DAC is an amazing place for designers, EDA professionals, and designers of various aspects to come through.
I love DAC because it's kind of the one occasion in the year when you get to take your pulse on the entire industry. And obviously all the big companies are here, but there's always a lot of smaller companies that you've never heard of who are doing something, so it's interesting to find out what they're up to.
I come to DAC because it's the biggest shopping trip of the year for EDA tools. Now apparently IP and automotive, but I'm not an automotive person, so I don't pay attention to that. But chip design stuff, yeah, I pay attention to that. That's why I come to DAC.
A lot of information, a lot of technology, very interesting stuff going on here. So many interesting people to learn from, and the lectures and the talks are very, very interesting.
So we do a lot of presentations with customers. So our customers come in and give us like a 1-hour presentation on use of our tools and their successes. And so those have been a really successful thing we've been doing every year, and those have been really full.
We started out this morning. I actually gave a talk at 10 o'clock, and it was just basically standing room only. It was actually great, and we have talks scheduled every hour on the hour, and I'm actually expecting it just to pick up momentum as we go along.
I think the keynotes are pretty important because they're people who really know what they're talking about, have been in the industry for decades, 20, 30 years.
Coming to DAC is important to us because there's all sorts of decision makers here. The training sessions are awesome, and we just get exposed to all sorts of different industries and personnel.
I go to the exhibit booths to take a look at Cadence EDI. I want to see Project Novus, what's going on with that. I go to Mentor to see the the BDA stuff and see what's going on with that. I go back to Cadence to take a look at the Palladium tools.
I just got here, but I can't wait to go explore the rest of this place, check out some of the demos and the booths, and see what everybody has this year at DAC.
It is the one event that we look forward to all year long, to come to meet people, to gather, to see what we can do together.
This is the one occasion when you can get every single EDA company in the entire world in one room and go and talk to all of them. And that doesn't happen any other time in the year.
Well, I think everybody should definitely attend, whether you're in the CAD tools business, the ASIC development business, or in board level and system support business like us. There's something for everyone here.
Good morning. Please welcome to the stage Soha Hassoun, 51st Design Automation Conference General Chair.
Good morning, everyone. I hope you're enjoying DAC. Today we have several Sky short keynoters. We have several sessions spanning all the tracks, so please make sure to attend those. Our next speaker is going to be Dr. Kareem Arabi. Kareem is a Vice President of Engineering at Qualcomm, where he's responsible for research and development in ASIC and new product development. Previously, he was VP of Engineering and Technology at Dialog Semiconductor, responsible for driving overall technology and new product development. Kareem had technical positions at PMC Sierra and Cirrus Logic and was co-founder of OpMax, an innovative startup in analog design, test, and automation. Kareem obtained his PhD and MS in electrical engineering from Polytechnique Montreal and his bachelor's degree in electrical engineering from Tehran Polytechnique. He's interested in technology development for mobile computing and all aspects of mobile SoC design and development. Kareem has published more than 100 papers and holds several patents covering key SoC design technologies. Please give a hand welcoming Kareem to the stage. Thank you.
Good morning, everyone. Thanks, Soha, for the wonderful introduction, and thanks, Lip-Bu, for the great note. It's such a pleasure to be here amongst the EDA community. I'm not new to EDA community and this conference. I have attended actually DAC since early 90s on and off. And whenever I think about DAC, two things crosses my mind. One, excellence in quality, and second, a conference that successfully gathered people from different segments of our semiconductor industry, all the way from fab to EDA to design and manufacturing and test. So people every year gather together and they share their ideas and innovation and they look forward. And that's what enables our industry. And another thing that crosses my mind is that DAC is one of those conferences that successfully balance the academia and industry very well. And that's demonstrated by excellence in quality of a wide array of technical paper and a vibrant exhibition hall that is come to be the pulse of our industry. It shows actually where the industry and EDA is every year. So DAC is a great place to be, and I'm delighted to be here to offer the keynote today. Now, having said that, still, I actually started my career almost somehow in the EDA industry. During my PhD, I worked on mixed signal design, and then I came across some IPs about mixed signal design and test automation and mixed signal design and test itself, and very quickly learned that if you want to, so I was very interested to see it in action, so we decided to co-found a company. And then selling a solution, the easiest way to automate it. Now, that was a wonderful experience being in EDA and IP and EDA. I learned a few lessons around then. So one was, it's really hard to sell high-tech solution to high-tech people, and you all know that. So that's really hard because you're trying to tell really bright people how to do their job better and how to enable them. And they're extremely critical because they know exactly what they want. So I know how difficult EDA industry is. Another thing that I learned is that I always knew that you can't be late to the market, but I learned that you can't be early to the market either. So it was 20 years ago, we were talking about, it was probably one of the first tools in analog design and test automation. So it was quite foreign to a lot of people. We used to do a lot of tutorial and convincing people. People will get excited by it. But it was really hard to get traction. Our analog IP, fortunately, got a lot of traction at the time. And then we were fortunate, within 2 years, our company was acquired. Then I went into semiconductor industry from mixed signal design, digital design. I took over management position. I managed EDA as part of my responsibilities in the past. Actually, one of the responsibilities that I had at Qualcomm few years ago was managing the EDA department. So I was there, working very closely with many of you, and I know how critical EDA industry is to the success of semiconductor industry. So this is an industry that works really, really hard, and then it works really hard, and it enables all these wonderful solutions. And it's really hard to imagine, what we would have been without EDA. And every year I had to go and defend our budget, and obviously finance is asking what value is bringing, and that was the easiest thing, because you paint a picture without EDA, what happened and how many years, probably hundreds of years that it takes to design a chip. So it's really easy, and it shows the testaments of what EDA can do for our industry. Now, one thing that EDA, amongst the things that enabled, and it was at forefront of that innovation, was mobile computing that really transformed our world. And now I'm here today to talk about mobile computing opportunities, challenges, and technology drivers. My talk has a couple of aspects. I'll talk about high-level stuff, and then I go into detail, so bear with me if I bore you with some of the slides. So it's a balance between the two. And I'm trying to hopefully cross the point what mobile computing is and what the challenges are and where we need to work on from here. So having said that, so mobile computing actually emerged to be the largest technology platform ever built by mankind. Today, there are an estimated 7 billion devices, connected devices out there, while the estimation of world population is about 7.2 billion. Fortunately or unfortunately, in some places in the world, more people have access to mobile devices than running water or electricity. Now that created a huge opportunity. That created a platform for innovation and reach like no other technology platform in our history. It is creating new businesses. It's transforming the way that we do things. We do business. We live. We study. We experience things. And our expectation is that this will clearly continue. Now, to put that into perspective, we had a wonderful growth, but the growth is continuing. Actually, the estimation is that between 2014 to 2018, there will be 8 billion new mobile devices shipped. And so the rate of progress, the growth of smartphones itself will be 20% in the next 4 years. So it's still growing quite fast. Now, to put that into perspective, to see what is mobile scale, between 2013 and 2017, the number of smartphone and tablets shipped, it will be more than the total number of all the consumer devices, all the way from PCs to set-top boxes. So it's a huge platform, and that's why mobile computing is a place, because of the scale that it has. It has the ability to transform the cost structure and enable applications that were not enabled. There are a lot of applications that they used to use sensors and gyros, and because they're so expensive, they used to cost $500 or $1,000 because integrating all these sensors are extremely expensive. But now that you have the mobile scale behind this technology, you can do the whole thing within a few dollars. So mobile, not only it enabled mobile computing, it enabled adjacent markets, and it enabled the R&D to put R&D behind these solutions so that we can do more things with these solutions. Now, with mobile devices, it came the data challenge. So we are all familiar with Moore's law. There's a data law that we say that the data density goes up 2x every year. So every year, our data density or demand for data is going up 2x. So in 2000, we said that by 2010, which means that in 10 years, the data density should go up by 1,000x. So that was a challenge. So we set our goals at Qualcomm to enable the 1,000x challenge. And interestingly enough, now we are at the beginning of 2014, and from that point, the data density, went up 49x already, and we are up there to really be in line with this challenge. Now, at some point, cell phones were used mostly, for communication. Now, from the early cell phone to smartphone today, there is about 50x more data that is being communicated. So they are becoming a data-centric devices. And then at some point, even today, our cell phones are mostly for pictures and email. But the estimation is that by 2017, 2/3 of our video will be transferred through mobile. So video takes a lot of computing and a lot of bandwidth, and that's driving. And then by 2020, actually the estimation is to have 25 billion connected devices. So these are connected devices that they're mobile. They don't need necessarily to be a cell phone. They could be a tablet or wearable. And when you multiply these two together, you could easily see where this 1,000x comes from. Now, one thing that I wanted to touch upon is cloud. Cloud has been a wonderful experience as well. Now, cloud has connected many services together, and what it has driven, because of cloud, now you have access to big data. So you have abundance of data, and then when you are in the cloud, you have abundant computing. So there is no bound to what you can do. You have enormous amount of data, history, and then you have enormous amount of computing power. So cloud computing has been very important in what we do today, and it's enabling a lot of application. But it's not taking away from mobile computing. They actually go hand in hand. So in contrast to big data, there is this notion of instant data. So these are data that are generated by user as they're interacting with their mobile devices, or they're gathered by the sensors that are connected to your mobile devices. So these are instant data. And they're real-time application that they cannot afford the latency of going to cloud, which could be few seconds. You need to process the data instantly. So these are instant data for real-time application. And that is driving mobile computing, which we call computing at the edge. So mobile computing and cloud computing will go hand in hand. Cases that you don't care about latency, you do the computation in the cloud. And cases that are driven by instant data and analytic of instant data, they will be driven at the edge using mobile computing. So the mobile computing and demand for mobile computing will keep growing. Now, there are a lot of everyday you see new use cases emerging for mobile devices. So there are computer vision, computational photography, augmented reality, advanced cameras. You see actually 2 high-resolution cameras today in front, in the back, sorry, and 1 in the front. Soon you will see multiple array of cameras for depth perception and a lot of interesting things that you could do with your cameras. And then we moved not only from 1080p to 4K. So now we have 4K coming into phones. And all these things, they're extremely computing intensive applications. So that's driving the need for computing power. In parallel with that, there are health application, there are mobile payment application, and applications like this, the driving need for security, reliability, and reliable link. You need a reliable wireless link, and you need security. So not only we have to have abundant computing power, we need security and reliability in our platform. Now, another application that is emerging quite fast, it's always on, always aware, or we sometimes call it the digital sixth sense. So these mobile devices, they have a unique opportunity to aggregate lots of data that they were not available to get in the past. There are input from sensors, there is GPS, there is Wi-Fi, there is wireless, there is user interaction. So these mobile devices need to fuse all these data together, and then they need to discover patterns from these data. They need to recognize what you need to do or what your intentions are. They have access actually to your calendar. They know about your meetings. They know about your travel plans. They actually know when you're driving because they have gyro and all these interesting sensors. So they know when you drive home, when you drive to work. And so they have all the information, and they can collect more, and they can anticipate basically what you are about to do, and they can arrange your experience to optimize your experience based on that. So now, always on, always aware, it means that your device has to be on all the time, and obviously you want your device to last at least 1 day. So this is driving a huge demand for ultra-low power architectures. So you saw that we have to drive the computing power for all these video kind of application. Now security at the same time and reliability. And now you have to be always on and always aware. So it's actually creating, we are in the midst of new architecture for these kind of application. And even the mobile architectures that we had in the past, they're not enough to enable always on, always aware. So I mentioned the 1000x, so I wanted to touch upon a little bit on network challenges and drivers. So what we are doing to address the problems that we have. So there are 3 strategies. One, we leverage wider bandwidth. So what we do, we aggregate different carriers. We have different LTE, 3G, 4G. You could have unlicensed. You can have Wi-Fi. So we're working really hard to aggregate all these things. And when you aggregate different type of data together to enable higher data, you have to worry about interference cancellation. You have to worry about power. So they're posing interesting challenges to our modem design. And we are really hard working on that. The other one is to get higher spectral density per megahertz or per hertz. So the other one was just aggregate and get more bandwidth. And then you have to get more out of your bandwidth, your single bandwidth. So there we are investing heavily on MIMO. You will see soon 8x8 MIMO on the downlink. You will see 4x4 on the uplink. And MIMO is extremely important to do interference cancellation and improve the efficiency of your bandwidth. And then the last but not least is HetNets. So we are investing heavily on smart cells. So these smart cells will be everywhere, and they will aggregate the data, and then they communicate to towers. So HetNets, it's extremely important to give us more spectral density. So what HetNets do, they give you more bit per second per hertz per square kilometer. So you're on the same area, you're getting more bandwidth. And together with this three strategy, we see that we are on track to sustain this demand of 2x data growth every year, and then 1,000x by 2020, starting from 2010. Now, so that was on the network side. Now we have, again, mobile devices. They're an aggregator. They're aggregating different technologies. So we have architecture challenges and drivers that I want to talk about. So mobile, as I mentioned, it's becoming a center of gravity. It is the conversion. It's one device that you remember at some point we had independent GPS devices. So we had different type of devices. So it's aggregated all these devices in one device. These days, people are not even carrying cameras. So it's becoming an aggregate devices, and it's providing this unique opportunity that no other devices in the history had, that not only it has great computing, it has great connectivity. These two are by themselves, they're creating a lot of opportunity. But then you have sensors, you have interaction with user, you have voice. So you have all these good technologies, but then that becomes a challenge because now you have to integrate a wide array of different technology on the same chip at extremely low power and low cost as well. Now, just to give you a little bit of complexity, this is one of the latest chips that we commercially released. This is commercially released, so you can imagine, the chips under right now, how complicated they would be. And the message that I wanted to pass is that not only we have connectivity for 4G, 3G, and when you talk about connectivity, you have to backward compatible because there are areas that in the world they have 4G, they don't have 3G. So your modem has to be backward compatible. Not only it should have the latest and greatest of 4G LTE, it should have 3G and 2G. Now you have to support Wi-Fi at the same time, and Bluetooth LE, and Wi-Fi you have to go to the latest and greatest, like right now AC and AH and so on. Because it becoming the main connectivity devices. So you have all this complexity on your modem itself, and then you have camera. You all noticed that there are phones with 20 megapixel and higher. So you have to process this information in real time. So you have camera engine, you have display. I mentioned 1080p. Now we have 4K, and some of you guys may think we are crazy to put 4K in a mobile devices, but it's not about what you're projecting on your screen of the mobile. Mobile is becoming the profile of choice, the platform of choice. You need to be able to project from mobile to any display that you find around yourself. So that's why you need to support 4K. So that requires video display, and then location is extremely important. Again, mobiles are traveling with you, so it's not enough to support GPS. You have to support GLONASS and other standards across the world. So you have to be all-inclusive. Then you have to have all these processing power with our Snapdragon processors. And then we have our own Adreno CPU, which is doing quite well. And CPU is, by the way, one of the areas that performance is going up exponentially. So you see, it's easy to see from one generation to another generation to the performance to double or sometimes even more. So that's growing quite fast. And then we have multimedia, an array of multimedia accelerator like video core and then audio and gestures. So all these cases I'll mention, they will need their own cores. And then sensor core. We took the initiative to integrate a sensor hub in our chip so that you can take all these data from sensors around you and fuse them with everything else that you have within your SoC. Now, to drive the point of mobile complexity, so I tried to look at the evolution of, for example, total gigahertz. And when I say total gigahertz, it's number of cores multiplied by gigahertz per per core. So total gigahertz, I'm comparing leading laptop with leading mobile here. So you see that it's saturating in laptop, and in mobile it's accelerating. I believe today we are almost at par, and then we are on track to exceed laptop capability in terms of total hertz. And then in terms of DDR speed as well, the same thing is happening. We are actually about to catch up with laptops, and we are on track to exceed that. So future devices, they will see 50 gigabytes per second of DDR speed. So now, the reason I mention that is that we need to provide the computing capability of a laptop in a form factor of a cell phone with a power budget of a cell phone. And not only that, we have to do more. Laptops don't need to have multiple cameras. They don't need to have sensors. They don't need to have GPS. They don't need to have all these wonderful connectivity links. So it drives the complexity that we are dealing with right now, and it is growing. So as a result, we have troubles. There are issues with our design. One is power management crises. You see that actually lithium-ion battery is improving. Actually, surprisingly, they're improving 20% a year. We feel that it will continue for another 4 years, and then it will saturate. People have to find another. But now, our power demand is growing faster, so it's creating a gap between the two that we need to address using clever power management solutions. And I show that when we were in 2G land, 1 watt was enough for a cell phone. At 4G, you need almost about 10 watt in peak. So we need to deal with power management crises. Not least important is thermal crises as well. So thermal envelope, we happen to have a standard that the temperature of your skin temperature of your phone should be around 45 degrees of Celsius, which is 20 degrees of Celsius above ambient. And then the chip itself, at junction, it should not be higher than 125 degrees of Celsius, otherwise you will damage your devices. So you have to manage both, not just we used to mostly worry about the junction temperature. Now we have to worry about skin temperature of the phone because you don't want to burn people's skin. Or you don't want the phone to be uncomfortable when you're handling it. So that's creating a huge crisis because you cannot have fan. You know, the form factor is very small. You cannot have large heat sinks. So there's a lot of research going on. So these days, in a lot of cases, you cannot actually unleash the total computing power that is available to you in your mobile devices. It happens that you heat up and you have to throttle back. So then throttling algorithms and ways of thermal management becoming very important. So what we do, we manage performance, power, and thermal at the same time. Otherwise, you leave performance on the table. Now, I mentioned that it's not enough to have a very fast processor on the device. And the reason, again, is power efficiency. If I could afford to be generous with consuming power, I could get away with a very simple architecture. But because I cannot do that, we have to be quite creative. So this, it just draws the point on coding, video coding. So you see that on 720p standard, we came up with a video core that gave us 3x power reduction. So we had to put a dedicated video core just to reduce power for that because we couldn't afford to pass that through normal APQ. Then on 1080p, that power reduction opportunity became 8x because the same thing that created that opportunity, it expanded. So now we have 8x power reduction by using a video core rather than other computing platform that is available in mobile devices. And 4K, actually I say non-available because it wasn't actually possible or practical to use a normal processor for 4K processing. So not only the need for these custom accelerators or hard accelerators, it's there, but it is expanding as well. And as an SoC architect, you have always this challenge, what are the number of cores that you need to have and how to partition the workload on these platforms. So you see that there are examples that you prefer CPU. There are examples that you prefer GPU, and there are examples that you prefer DSP, for example. In this case, 2D to 3D video compression works better on CPU. Image processing and denoising works better on GPU, obviously. And then character recognition and gesture works better on DSP. And these pictures change a little bit. You have to adjust your core. So it's a constant challenge to find out, do I have the right computing power within my mobile devices that can service the need, the user need. And so there is a lot of work that is going on modeling and then workload analysis to analyze this. Now, one thing that I want to mention is brain-inspired computing, because I talked a lot about power, and we think about how to reduce power. And obviously, we looked a lot on brain and see how we can inspire from us. Here, I compare human brain with IBM Sequoia. So IBM Sequoia is the third fastest supercomputer in the world. Now, I gave you homework. You'll go and find out who are the fastest and second fastest. But I know IBM Sequoia, so that's why I put it here. So IBM Sequoia has 1.6 petabytes of memory, 16.3 petaflops of computing power. So that's floating operating per second. And then it consumes about 7.9 megawatt for that kind of computing power. Now, human brain has 3.5 petabytes of memory. Again, we don't know human brain. We don't know what is the concept of memory and computing. So all these things are inaccurate, but bear with me, just a compare point to draw the point. And there is a lot of controversy. What is the human power? Some people say 20, some people say 30, 10, depending how you calculate it. So just bear with me on that. But 20 petaflops of computing power in human brain at 20 watt. So it's extremely power efficient, and we try to understand why is our brain so power efficient. And the answer, brain is a massively parallel computing device. It's a computing engine. It has about 86 billion, some people say up to 100 billion, but 86 billion neurons that are doing computing independently. It has no system clock. It's an event-driven system. So it works when there are stimuli, and then it doesn't when there is nothing. But there's always stimuli because our brain actually never shuts down. Even when we sleep, there are senses that are coming in. Has no hardware-software distinction, which is very important. You can't find where is the hardware. They're all together bundled. It's one system, one network. Performs processing and memory by the same components. So there's no memory and computing distinction. Well, there is a little bit. Some people say that the memory is in the synapses and the computing is in neuron. But there's really no clear distinction there. And then it's a self-organizing, self-healing system because they make it massively parallel. When you're massively parallel, you fail. Actually, all of you guys lost thousands of neurons since I started my talk. So it reorganized itself. So it's a self-healing system because when you make it 86 billion, you cannot guarantee that everything. So it's not like one of your memory bit is corrupted and your whole operating system is shuts down because it cannot find the right command there. So it self-organizes generously. And so these are lessons that we are learning from mobile computing and from brain, and we are trying to apply it to mobile computing. Now, I will go and delve into deeper a little bit and talk about technology challenges and drivers. So I just go through this quickly. I don't want to spend much time. But one of the biggest problems is cost. We are a consumer. Mobile computing goes to consumer, and cost is extremely important. We are very cost sensitive. And Moore's law has been great. But the problem is, although we are still scaling down, the cost benefit is not there anymore. So the economic aspects of Moore's law is stalling, which is really creating a big problem for us because we used to stick more functionality in our devices, make them more wonderful, and then sell them for almost the same price. It's not happening anymore. So that's a big problem. Other side problems are DRAM is approaching its scaling limit because you cannot scale capacitors more. So again, same thing. They're getting more expensive as you demand for bigger DRAM. So that's a big issue. And then escalating cost of chip design. We need to assemble bigger and bigger design teams to design our chips. So that's becoming a big problem. And you see that a lot of people are exiting this because it's quite difficult to keep up with the complexity and have the right design team in place. Now, performance, I already talked about thermal limit. It is actually a bottleneck. It is something that is limiting our performance. We see memory bandwidth is very important for our performance because a lot of graphic data, it goes to memory. So memory bandwidth is very important, and we see that our memory bandwidth through DDR is saturating by clock speed because you cannot clock them faster, by power envelope, obviously you cannot consume a lot of power, and then the number of available pins. So memory bandwidth is another big problem that we need to work on. And then power distribution network. As you are shutting down and bringing up all these data, your power network is changing aggressively, so that's creating a voltage drop, which is really bad for time enclosure. So power distribution network becomes another big problem. I talked about complexity, so I don't want to repeat that, but complexity, again, we are dealing with a platform that is getting more and more complex for good reasons, by the way. So now, technology drive is obviously CMOS scaling roadmap, working with our EDA partners and fabs, and we have been successfully able to innovate this scaling roadmap. So you guys recall that we did strained silicon in 2005, and then we did high-K metal gate and new metals gate stack in 2010. Now we're working really hard on FinFET, and then some people are working on FDSOI. And then going forward, we see new channel, new properties in the channel. We see 3.5, we see germanium, and then we see that the need for a transistor, by the way, when you try to stack FinFET and thin it down, they become nanowire. So nanowire and all around will be there. But these technology will be probably between node 5 and 7. So it's coming, and we need to go there. So in this decade, probably we'll see nanowires and germanium or 3.5 in the channel to improve mobility. And then on the third dimension, actually, which is very important, is resistive memories, MRAM. You will see these applications emerging, not probably in mobile computing, but adjacent fields to mobile computing. They will emerge in the next few years. And then probably first MRAM and then resistive RAM. And then monolithic 3D IC. I'll mention why, but that's something that eventually it will happen. Now, when we talk about all these problems and challenges, people look at different, they go back to the table and try to find different components or different elements to build transistors. And everyone is looking at mobility. Design is not about just mobility. I need band gap, because mobility allows me to switch my transistor faster, but band gap allows me to shut them down and turn them back on. If I can not shut down my device, I cannot use it. So band gap is very important. And people are looking at graphene and molybdenum disulfate and all these great work. The problem with those devices, mobility is great, but then band gap, they have no band gap. So I cannot build an effective gate out of them. And what they do, they add impurity to address the band gap. And by the time they do this, the mobility comes down to even below CMOS. So I don't think that it will have anytime soon home in normal computing. I think it will have great potential for sensors, for sensor elements themselves, for transparent things, for flexible electronic, not for the processing, but for sensor element. But for processing and computing, I think we'll stay with CMOS-like devices. But if you look at the neighbor devices to silicon, like GaAs, InGaAs, and germanium, so to 45 channels, so we see that happening probably in this decade. Now, another big challenge that we have is interconnect. Interconnect is not scaling. So if you actually look at the blue curve, it sees that interconnect RC per millimeter square, it is inching up as we go to deeper technology. And that's a big problem because a lot of our design end up being interconnect dominated, while transistor has been itself scaling down quite nicely, as you see. So that is creating a problem for us because even we go to deeper node, it's not helping us. So we feel something needs to be done about interconnect itself. And what is done there is monolithic 3D. So industry has worked on 3D through TSS, through silicon vias. Through silicon via, it needs through silicon vias itself, and then it needs microbump. So in my opinion, it's competing with application where you need to replace IOs. So if you have chips that talk to each other and they need to go through IO, IOs are quite power hungry. So if you want to replace these kind of things, true silicon stacking is really good, and we see that emerging in a lot of cases like FPGAs. We see them in sensors, in camera sensors and stuff like that, or memory stacking because otherwise you had to have different memories. But then they're not solving really the interconnect issue that I talked about, and they're costly. So we're looking at true monolithic 3D where you truly put, so you don't have the notion of TSV, you have normal vias between different stacks, and then the interconnect between different layers will be smaller than your interconnect at 2D. So, and that's the paradigm, that's the inflection point. If you can come up with a 3D solution where your interconnect going between different layers, delay becomes smaller than the long interconnect that you can have in 2D, then 3D becomes viable. So we're looking at monolithic 3D. Again, this is kind of end of the decade. We see the potential for this technology to have millions of inter-tier vias per square millimeter. It can actually give us one process node advantage. We estimate 30% power saving, about 30-40% performance gain. Footprint reduction, obviously, because you're stacking, and that's if you just stack 2 layers, and 5-10% in cost reduction. So that's an important driver as well. I mentioned memory, so I think there should be a lot of research on DRAM, on embedded memory, both for power and density and viability. One area that we are working very hard is MRAM. So MRAM, if you compare to charge-based devices, so MRAM, just a very quick thing, normally memories work based on charge transfer. MRAM is based on spin of your electrons. So spin of electron, it could be your logic state, depending what direction they spin. And by injecting current, you can change the spin. So basically, you let it spin in one direction, that could be 0. And then if you inject enough current, you can inverse the spin, and then it becomes 1. So you can distinguish between 1 and 0. And depending if you have 1 or 0 in the MRAM, the resistance can change. And by detecting the resistance, you can know if you have 0 and 1. So it's quite simple, but it's not easy to manufacture. So we have been working quite hard on that. So I'm comparing it here by the latest CMOS bit cell. And you see that you have in-plane MRAM and then perpendicular MRAM. The advantage of MRAM, when it's non-volatile memory, and then the standby current is almost 0. So you can program it and leave it there and consumes no power, which is great. But then read-write is still not good. You see in-plane, it's a little bit more power hungry when you read and write than SRAM, but then perpendicular, not only it's smaller, but it consumes a fraction of power in read-write, but then retention power is almost 0, and then the density is much better than SRAM. So, but then speed is still a problem, and we are working the yield issues. And then there is another category that we are working that actually promising to be 5 to 10x better than perpendicular MRAM. That's kind of 10 years out, or 5-10 years out. So this is a promising area again. We used a lot of low power techniques in mobile platform, all the way from multi-VT, clock gating, power shutdown. So everything that you can imagine. And one of the biggest disciplines that goes on when you design these mobile devices is power. Every gate is scrutinized for leakage, for power. So voltage island has been a very successful solution, actually. So what we do, we normally divide our chip in different voltage island, and we give them a separate voltage that come normally from outside. So you see all these blocks, they may have different island. And these islands, it allows us to independently shut down. If I don't need a core, It's because mobile is a true heterogeneous application, which means that in some of the use cases, you may not need all the cores that you have. You're not dealing with video. Video engine doesn't need to be up. So this allows us to shut them down independently. So it allows you, even when they're not shut down, to have independent voltages for all these domains. But you need to put level shifters so that you don't run into reliability issues. So that allowed us to reduce power by 25 to 50%, probably even more. Now, what is emerging is embedded voltage regulators. So some of the PMIC functionality is moving on chip, and that has additional advantages. It enables more granular voltage islands, so you're not, because before you were limited by the number of power domains that you can have from outside. This thing will be not unlimited, there will be some cost limit, but you can go more granular. Because your power management is on chip, you can have faster transition, and when you have faster transition, there is a lot of opportunity that comes from that. Your power mesh becomes simplified, the amount of decap could be smaller, and then basically you can have more opportunity to shut down and power up, because a lot of cases, if you're not fast, you just let go. If you can quickly power on and power down, you have more opportunity to take advantage of that. It reduces margins that account for voltage drop from internal voltage all the way to the PMIC, because you don't know what is the voltage drop, and you have all these LDI over DT. You typically margin, when you bring it on chip, you reduce that margin. So as a result, it results in a considerable additional power saving and performance improvement as well. So I talked about Moore's law, and Moore's law, in my opinion, is a self-fulfilling prophecy. It's really a goal for the industry that says that, hey, let's go based on some empirical, observation actually, but industry is challenging itself to say, okay, I need to improve density by 2x, every 2 years, or whatever it is. So we'll all work together and synchronize ourselves throughout this semiconductor industry to make it happen. And because it was easier to do this with node scaling, the innovation in architecture, for example, I'm speaking on my behalf, on architecture and circuits slowed down. But now that node scaling is slowing down, at least the economic benefit of that, we need to turn on the other aspects of innovation. It's a cumulative thing. It doesn't need to be just node scaling. It could be architectural innovation. And to say least but not least is EDA. EDA enabled this industry. So I think it's time for EDA to really boost the innovation cycle to basically compensate for this slowdown. So if you see that I tried to go and look, and it has, forgive me if I'm not right, but I looked at main innovation that happened. I call them disruptive innovation. The first one, Silicon Compiler, you guys remember in 80, 81, that these guys, before that, people used to push polygons by hand. These guys, they came with a tool that gives you a layout automatically. That was great. It cut the design time from 3 years to a month, actually, at the time, I remember. And then all these good stuff, RTL and logic synthesis. Verilog, just to capture a design in Verilog rather than drawing schematic, it increased the amount of design that we can do and archive them and automate them. It provided the platform for automation, just the HDL, Verilog, gate level, I'm not even talking about, and that was driven by Verilog. And then it continued with VHDL system, Verilog, and so on. And then you had STA, you had RTL synthesis, you had DFT and ATPG, which if it was not in place, you would spend 3 years, 4 years, just test one device on a tester. So it was great to enable us to really go to mass production. Design for manufacturability emerged, and then RTL simulation, formal equivalency, and hardware-assisted verification. So these are all disruptive innovation, and in between, a lot of incremental innovation happened. Right now, we are working hard on high-level verification languages, formal verification, and a lot of other solutions. ESL is still there. It's gaining traction, but it's still there. But really, we need to turn on the innovation. Now, I was trying to see what we should do by 2010. So by 2010, we will have 10 billion transistor in our devices. Right now, it's around 2. the premium devices. So it's easy to imagine 10 billion transistor in 2010. So we need to be able to manage that. I think software, hardware co-design has been always a problem. We have talked about it, but I think it's about, and Wally was here, he talked about going and taking on different budgets to increase EDA, and that's a good area to go and really invest. Because still, especially in mobile, we have those heterogeneous computing and software, hardware, it's extremely challenging right now. But what we need really going back up, 10 to 15x gain, that's X, in designer productivity. It won't be possible to just scale up and increase the number of designers. So we really need, EDA enabled us to design more chips with less people. We need to accelerate that again. We need 5 to 7x reduction in power consumption. I really want my mobile devices to last a week, and it's partially driven by that. 50 to 60% in area reduction. And again, these numbers, it's really looking at the slowdown in technology node and what EDA can do in the next, until 2010 to compensate for that. And I know that we will accelerate our architectural innovation, as you have seen already. But 2x reduction in overall design cycle, again, that's very important. And I mentioned the complexity there. So we really need more innovation, more disruptive innovation. And I feel these things are possible. I think we have one of the best talents of the world in EDA industry. So I think we can do it again. Again, I would like to conclude my talk. So I just wanted to drive the point that mobile computing is driven by several emerging use cases that they continue. And it is still growing. It's really continues to grow. It will continue to drive increased requirement for processing and integration while maintaining lower power. So it's two conflicting things. We need more processing power, but at the same time, we need to get lower power. So that's a big challenge for any SoC architect or any designer. We need solutions for economical integration, and memory becomes one of the bottlenecks, either in memory itself or bandwidth. So we need to focus on integrated hardware and software solutions. So that's really about time to do that. And that will define our success. And again, we shouldn't forget about the need for peak data rates and then security and reliability that, again, are driving mobile system. Anyway, that concludes my talk. Thanks for your attention.
Thank you very much for a wonderful talk.
Thanks,
We appreciate your faith in EDA.